Okay, so this is 5.2, double integrals over general regions. We'll see how far we get. If we have to pick up and do a part 2, we can. Or I might do one of those things where I stay on and finish it just so it's all done. And then you guys can always watch the remainder later. You can see your learning objectives. The first one cuts off a little bit. You'll see it a little bit better in the PDF. I'll try to get everything up kind of soon, probably before the weekend. All right. We have some definitions. Right. So let's dive right in. Do apologize if I get a little bit quicker. I just don't want us to take a while on it. Okay, so when describing a region as type 1, we need to identify the function that lies above the region and the function that lies below the region. Here, region D is bounded above by y equals the square root of x and below by y equals x cubed. In the interval for x in 0 to 1, hence as type 1, D is described as the following set. So type 1, D would be x, y, 0 to 1, x cubed, square root of x. Now, however, when describing a region as type 2, we need to identify the function that lies on the left of the region and the function that lies on the right of the region. Here, region D is bounded on the left by x equals y squared, and on the right by x equals the cubed root of y in the interval y to 0 to 1. So as I type 2, you would have it described as xy and it would be, this time the y is nicer looking. Okay. All right, theorems, our favorite part of calculus. Getting some tools in our toolbox. Go ahead and all right. Okay. So we want to evaluate the integral where D is shown in figure 516. You get to see it first. You'll notice that for a lot of these examples, we have a figure that we're given, and then we have to figure out the integral based on that figure. But at least you don't have to draw it. So that's a plus. All right, so D, in this case, we're going to have xy, where x is 0 to 2, and then y is 1/2 x to 1. So then if we do the double integration over region D, all right, so if we work that out, we would have, so 0, 2, and then I'm going to go ahead and integrate, kind of skipping a little bit of a rewrite. So if you do that integration, you get which if you plug everything in, you just end up with 2. If you need some extra notes, the first step, we integrated the integral for a type 1 region. So that would be the step type 1 region. Then we integrate with respect to y using u substitution, where u equaled xy and x is held constant. And then for the second part, we did u substitution, we have u 1/2 x squared. So some of these you're going to have to brush up on your u substitution if you need to. So I think they just broke it down a little bit here, and I just wanted to show you what the textbook had. But we obviously wrote through it, so you can have that too. All right. So this one says evaluate the integral, and it gives it to us, and it tells us where it's at. So this one's a lot more straightforward. It is a gross answer at the end, but all right. And these kind of help you out a little bit. And then you can see there's some extra notes down at the bottom. I don't know if we're gonna have our answers line up with that, but you'll be able to kind of see where they go. So the first thing we're gonna do is we're gonna integrate with a type 2 region. So it's going with this second option there. If you want to rewrite, and you can, then we're gonna go 2 to 3 for the y, and then x is y squared minus 3 to y plus 3. And then 3x squared plus y squared dx dy. We want to integrate with respect to x first, I guess I should say. So 2 to 3, and then x cubed plus xy squared dy. Oh, I forgot our bounds. All right, and then here comes part of the gross part. You have to then plug everything in. I will write it out for you this time. I don't know if we really need to, but I will. Sorry. Okay. If you work that out, you're gonna end up. Oh, my 2 is negative the whole time outside here. Sorry. I was so used to doing positives. So if you work that out, you're gonna end up with 54 plus 27y minus 12y squared plus 2y cubed plus 8y to the 4th minus y to the 6th dy. And then if you do that integration, sorry, to do that integration, you're going to end up with 54y plus 27 over 2y squared minus 4y cubed plus y to the 4th over 2 plus 8y to the 5th over 5 minus y to the 7th over 7, negative 2 to 3. If you work all of that out, you end up with 2,375 over 7. Now, if you gave me the decimal version or you gave the homework the decimal version and you find out they wanted the fraction, and for whatever reason, the very intelligent computer system didn't accept it, just let me know and I will give it to you. But, all right. Here's a nice little theorem for you. I'm super duper hoping that we don't have to do any extra slides because we only have one slide available. All right. All right. So example 514, decomposing regions, express region D, shown in figure 519, it's there for you, as a region, as a union of regions of type 1 or type 2, and evaluate the integral. So the region D is not easy to decompose into any one type. It's actually a combination of the 2 different types. So we can write it as a region of, as a union of 3 regions, D1, D2, and D3, where we have the following. This gets kind of gross. All right, so get ready for it. Now, they just mentioned about a D3, but I don't see the D3. We even bring down, so I'm sure it's there. Yes, it is. It just doesn't tell us what it is. All right. So I'm going to make this a little bit bigger. You can find it in your textbook. So D1 will be XY negative 2, X is 0, and then 0 to X plus 2 quantity squared. That's D1. D2 is going to be 0 y to 4, and then 0x to y minus 1 over 16 y cubed. All right, and then take a look at this guy. It is showing you that third region. Right? So here D1 is type 1, and D2 and 3 are both type 2. So type 1, type 2, and type 2. It tells you as well, but whatever, I wrote it. So we have over D 2x plus 5y dA. And now we're going to have the 3 different regions. Going to try to skip a little bit of some steps. So if you go back through and you don't understand it, check out the textbook. It's -2 y minus cubed. You can see why they didn't write D3 out, because it's pretty similar to D2. It just goes, instead of starting at 0, it starts at -2. But otherwise, it's the same. All right. So now what we would do is start integrating and throwing some stuff in. So -2 to 0. And we would have 1/2 2 plus x squared 20 plus 24x plus 5x squared. That's after you integrate for the first part and plug in. So that's the step that we're on. It's 1 over 256 y to the 6th minus 7 over 16 y to the 4th plus 6y squared and plus -2, or sorry, that one's going to be -4 to 0. And then that one is very similar, 1 over 256 pi to 6. It's actually the same. It's very nearly the same. Okay, so if you plug everything in after you do the second round, you end up with 40 over 3 plus 1,664 over 35 minus 1696 over 35. And that overall answer gives you 1,304 over 105. If you wanted to try doing this again, there is a checkpoint in your textbook where it says you can redo the example using a union of two type 2 regions. So that's up to you. I'm not going to do it in the slides. Okay. All right. Changing the order of integration, reverse the order of integration in the integrated integral, then evaluate the new integrated integral. So we can see from the limits of the integration that the region is bounded above by y equals 2 minus x squared and below by y equals 0, where x is the interval from 0 to the square root of 2. I'm going to assume that this little graphic helps you see what I'm saying. Yep, it do. Okay. By reversing the order, we have the region bounded on the left by x equals 0 and on the right by the square root of 2 minus y, where y is in the interval 0 to 2. So we solve y equal to 2 minus x squared in terms of x to get x equal to the square root of 2 minus y. That tells us we can then do 0 to the square root of 2, 0 to 2 minus x squared, xe to the x squared dy dx. All right, so now they want us to switch it around. So we're going to end up with 0 to 2 and 0 to the square root of 2 minus y. And it's going to be xe to the x squared dx dy. So we want to reverse the order of the integration, then use substitution. So we would have 0 to 2, 1/2 e to the x squared from 0 to the square root of 2 minus y dy. And then I'll try to squeeze it all on here so you can have each piece. 1/2 e to 2 minus y minus 1 dy equals negative 1/2 e to 2 minus y plus y to 0 to 2. Oh my goodness, can't get that part to save my soul. So then you end up with an answer 1/2 e squared minus 3. Again, I apologize if I'm going a little bit quick. My throat is just on fire. Trying to just get it on the video for you. All right, so evaluating an integrated integral by reversing the order of integration. There's a part A and a part B. This is going to focus on the part A. Part A. And the next slide is going to focus on the part B. One way to look at this is by integrating y from y equal to 0 to y equal to 1 minus x vertically, and then integrating from x equal to 0 to x equal to 1. So we're going to go with our region, and obviously that's where you start each time. All right, so then 0 to 1, 0 to 1 minus x, and it's x minus 2y dy dx. So 0 to 1, xy minus 2y squared, 0 to 1 minus x dx. We will do some substituting in, so we would get it x 1 minus x minus 1 minus x squared dx. So 0 to 1, negative 1 plus 3x minus 2x squared dx equals negative x plus 3/2 x squared minus 2/3 x cubed, 0 to 1. So you end up with negative 1/6. That part is a little bit nice. We like that answer. That's a nice common answer. All right, now we're going to integrate with respect to x first, and I bet you won't be able to guess what that answer will be. So, part B. The other way to do this problem is by integrating x from 0 to y minus 1, or y 1 minus y horizontally, and then integrating from y from 0 to 1. So again, we have to start with our overall statement. It's just going to be 0 to 1, and then 0 to 1 minus y, x minus 2y, dx dy. So then you have 0 to 1, 1/2 x squared minus 2xy, 0 to 1 minus y, dx. Nope, dy, sorry. But yeah, dy. So then if you sub in 1/2 1 minus y squared minus 2y 1 minus y dy 0 to 1 1/2 minus 3y plus 5 halves y squared dy, plug everything in, you end up getting 1/2 y minus 3 halves y squared plus 5/6 y cubed, 0 to 1, again, negative 1/6. Okie. All right, we're rolling. Finding the volume of a tetrahedron. I bet you didn't wake up this morning thinking you would do that. Find the volume of a solid bounded by the planes x equal to 0, y equal to 0, z equal to 0, and 2x plus 3y plus z equal to 6. This little image here is very helpful to you, so I give it to you. There you go. The solid is a tetrahedron with the base on the xy plane and a height of z equal to 6 minus 2x minus 3y. The base is the region D bounded by the lines x equals 0, y equals 0, and 2x plus 3y equals 6, where z equals 0. So hence the figure. Note that we can consider the region D as type 1 or as type 2, and we can integrate in both ways. I'm going to let you know that you end up with the same answer, either way you do it. And I don't know if we'll have enough room to do both on here. We can give it the good old college try. So let's try it. So first consider D as a type 1 region. And our D would then be so therefore our volume would be um, 6 minus 2x minus 3y dy dx. And then 0 to 3. Sorry, the day is getting long and my writing is getting weak. 6y minus 2xy minus 3 halves y squared, 0 to 2 minus 2/3 x d x. Okay, so 0 to 3, 2/3 x minus 3 squared dx. So then if you work everything out, you end up with a 6. And if we go with type 2, D, we have 0 y to negative 2, nope, to positive 2, sorry. And then 0 x. So in this situation, the volume is dx dy. So 0 to 2. 6x minus x squared minus 3x y 0, 3 halves y dy. So then that's 0 to 2, 9/4 y minus 2 squared dy. And if you work that out, you also get a 6. Therefore, the volume is 6 units cubed. Or you could write it out, 6 cubic units. But regardless, that is the answer. Okay. Definition is hard to see here. All right, we'll try it like that. You can see I was trying to really get some slide space because of the awkward layout that I normally don't use. We may run a few minutes over. I ask that as many of you stay as possible, but I understand. All right, finding the area of a region. Find the area of a region bounded below by the curve y equals x squared and above by the line y equals 2x in the first quadrant. So you can see the figure below. We just have to integrate the constant function f xy equal to 1 over the region. Thus, the area A of the bounded region is found by doing 0 to 2, x squared to 2x. I guess you could say 1 dy dx. Or you could flip it around and you could do 0 to 4 y over 2 and then the square root of y dx dy. Either way you do it, you should end up with the same answer. So area should equal over the region D dx dy 0 to 2 x squared 2x 1 dy dx. So 0 to 2 y x squared 2x dx 0 to 2 2x minus x squared dx. So that's going to be x squared minus x cubed over 3, 0 to 2, which is 4 over 3. Okay, that's the area. All right, we have another combo definition into the example. Sorry, there are a lot of examples in this particular section. All right, so first we find the area where region D is given by the figure. So we would have this part is equal to 0 to 1, 0, or y to square root of y, 1 dx dy. So then you would have x from y to the square root of y, 0 to 1, dy, 0 to 1, square root of y minus y, dy. So then you end up with 2/3 y to 3/2 minus y squared over 2, 0 to 1. So you end up with 1/6. Then the average value of the given function over this region is, and now we have to do the average. So we would do 1/AD. We just found A of D. So that would be 1/1/6, which is just going to end up being 6. 0 to 1, 7/2, because you're integrating that now. 7/2 x squared y squared from y to square root of y. dy. So you get 6, 0 to 1, 7/2 y squared y minus y squared dy. So 6, 0 to 1, 7/2 y cubed minus y to the 4th dy. So that's going to be 42/2 y to the 4th over 4 minus y to the 5th over 5, 0, 1. So you end up with 42/40, which is 21/20. I realize some of this you'll probably have to just write down and then go back over. So for this one, you'll probably need to wait for the PDF, but you can see there's an example on here. Most of the solution is nicer if you see it that way, but I am going to write a little bit for you. So you would have a 0 to 1, y squared to y, e to the y over y, dx dy, which would be 0 to 1, e to the y over y, x, y squared to y, dy. So 0 to 1, e to the y over y, y minus y squared, dy. So 0 to 1, e to the y over y. Oops, sorry. That part's gone now. We distributed it. So you get e to the y minus y, e to the y, which gives you e minus 2. And it goes with this answer. All right, it's very, very close to being done. I'm so proud of us. Here's another theorem mashed up with an example. So the region R is the first quadrant of the plane, which is unbounded. So we have this part, which we then say is the limit BD to infinity and beyond, 0 to B, and then 0 to D, x, y, e to the negative x squared minus y squared, dy on the inside, dx on the outside. You're going to rewrite that limit. I'm not going to. Please rewrite it. 0 to D. Now we're switching it a little bit. Yeah, we're switching them. X, y to the E minus x squared minus y squared, dy, dx, nope, dy, dy. So then, yeah, I would just bring that limit down, sorry. And then we're going to bring it down again. So 1/4 E, oh no, 1 minus E, 1 minus E to negative B squared. We're subbing in 1 minus E to negative D squared. And that's going to be 1/4. So therefore, the area, the double integral over the region is convergent. And the value is 1/4. All right. Very close to being done. If you're still with me, I appreciate you. If you had to leave, I'm sorry. You can get the rest of it, the last 15 or so minutes off the video when it's posted. Like I said, I'm just trying to do things a little bit quick. All right. So application to probability. At Sydney's restaurant, customers must wait an average of 15 minutes for a table. From the time they are seated until they have finished their meal requires an additional 40 minutes on average. What is the probability that a customer spends less than an hour and a half at the diner, assuming that waiting for a table and completing the meal are independent events? So waiting times are mathematically modeled by an exponential density function, with m being the average wait time. So that looks like the following. If t greater than 0 and if t, sorry, if t is less than 0. Okay, so basically if they don't go or if they walk in and turn around and walk right back out. If x and y are random variables for waiting for a table and completing the meal, then the probability density functions are respectively, which would mean that we would have, sorry to go Christmas. And then the second setup, okay. So clearly the events are independent, and hence the joint density function is the product of the individual functions. We have to set all this up and then still find the probability. So this is the one of the longer, probably is the longest example. So I'm probably gonna have to add my extra slide in right here. But so we would have then f of xy equal to f1 of x, and then f2 of y, 0, 1 over 600, e to the negative x over 15, and then times e to the negative y over 40. If x is less than 0 or y is less than 0. And then there are commas. Sorry. Okay. And then if x or y is greater than 0. We want to find the probability of that the combined time x plus y is less than 90 minutes. In terms of geometry, it means that the region D is in the first quadrant, bounded by the line x plus y equal to 90. So you can kind of see that. Hence, the probability x comma y is in the region would look like, so this is basically what our end goal is. We're looking for the probability of x plus y greater than or equal to 90. Probability x comma y is an element of D over D f x y dA. We got to keep it rolling. One over 600 e to the negative x over 15 e to the negative y over 40 dA. Since x plus y equals 90 is the same as y equals 90 minus x, we have a region of type 1. So type 1 d x comma y would be 0 x 90 0 y 90 minus x. Make sure you guys really understand how to do those parts, or it's going to end up really biting you when you do your homework. So in your test, p x plus y, greater than or equal to 90 equals 1 over 600 gets pulled out. Uh, 0 to 90, and then 0 to 90 minus x of our e to the negative 15, x on top, and then e to the negative y over 40, dx dy. So then 1 over 600 again. Uh, 0 to 90, and 0 to 90 minus x. Why are we writing that twice? I'm not writing it twice. That seems silly. We're just gonna go skip that step. I don't know why they have it twice and I'm not writing it, so 15 plus y over 40 dx dy. So if you do all that stuff, and possibly shove it into a calculator, you end up with 0.8328. And we have one example after this, so just one slide. And we're only a couple minutes over, which is great. So this means there is an 83.28% chance that a customer spends less time than an hour and a half at the diner. Last problem, last slide, last definition. Sorry, I don't have, oh, that's from the one before. Okay. So, and you can probably see this a little bit better in the, all right, I'm leaving that there, but you'll probably see it better in the PDF. So using the first quadrant of the rectangular coordinate plane as the sample space, we have improper integrals for e of x and e of y, the expected time for the table. So e of x over 600, e to the negative x over 15, e to the negative y over 40, dA. So then pull the 1 over 600 out, you have 0 to infinity because you could potentially wait forever to get seated and wait forever to finish your meal. Not that I think people would do that, but technically it's available. So 1 over 600. Do I have to do? All right. We're not going to do both pieces, but I will show you what the answer is for the second piece if you did E for the or E of Y. Oh no! Crazy. All right. Almost done. Apparently my tablet wants to be done. Okay, so right, so then we're going to split this. And I do recommend you try to do the y, x expected of the y on your own. All right. So 1/600. We're gonna barely have enough room for this. Here, 15 years. Oh, that is in X. I thought so. We're not. We haven't plugged in yet. We're going to plug in. Okay, so when you plug in, you get -15 e to the -a/15 x plus 15 plus 225, and the limit as b approaches infinity, -40 e to -b over 40 plus 40, no, 40, not 400. All right, so then you end up with 1/600 times 225 times 40, so that's 15. So basically you end up finding out that the expected value of x is 15. The expected value of y is 40. So if you do a similar calculation, you'll find that out. Do this calculation. You're gonna see you do very similar things. All right. So that is it for that lesson. I will try to get these up for you, but I am done for the day.